so this is the title, Nonlinear and Local Surfaces, Structure Problems and some of their applications, okay? And so, well, so then let's talk about, so what is a diffusion process? And, okay, so here are some stuff. So, so basically, as it says over there, right, we want to study the structure of some problem, of some surface, right? So we want to model then equations that vary in space and time. So here they are in space, and then we have to make variations of it, right, or probability densities, or speed of flow, or even body elastic equation, local diffusion equations, etc., etc., etc. Okay, so basically, let's try to look at this mathematics and see how it evolves. Okay, so as I said there, these models that in general that we are discussing is many times described using partial differential equations. Here I have the, here we have a case, right? And here I have another, right? This is a surface which is bent up in one direction and bent up on the other, right? And that has the property that when you put the tangent line at some point, right, the amount of that it bends down is equal to the amount of that it bends up. And therefore, if that's the case, then it satisfies an equation that basically says that the Laplacian is zero, because you lose half of the Laplacian down, the other up at the right times. Okay, so basically, oops, sorry. Which this? No. Yeah, okay. So this is the picture here, right? This way is bending up and down the same level, and so basically you have the surface has Laplacian equal to zero. So mean curvature. So what is mean curvature, right? That I'm saying mean curvature zero. Mean curvature is the sum of the principal curvatures model in the diffusion operator in divergence form. In other words, we have this diffusion operator is the same, the bending, what I was saying, that the bending is the same above and down, right? And so this measuring how is you bending, you have to do the divergence of the Laplacian, which is the divergence of the gradient of u, right? So that is what tells us how the bending is, right? If you take at a point the tangential surface, right, and then make that their basis, and then you, when you have here, your point now is tangential zero, and then you look at what happens with the Laplacian, that is the way that function is bending up and down. For instance, if this just bending down, the Laplacian is negative. If it bends up, the Laplacian is positive, right? And there is a combination, then you can have a family of right-hand sides, right? Depending, if you start from zero, negative, and then the way you bend up, you get positive, okay? So this is, as I said, is the Laplacian, is the divergence of the gradient of u of x, right? And it's nice to, I mean, really one would say, well, why don't you just tell me the sum of uii, right? Because in many applications, it is interesting when this is a divergence of some oscillation of the gradient of u of x, right? This is a family of problems which has some sense has many applications, right? Because it's not so flat as this, where the surface is so like this, when there are ingredients, right, for instance, in the quality of this quantity that is more interested, for in that case, you have to look at divergence of some quantitative gradient of u, which I hope may appear later. And the simplest one is this one, the Laplacian. Okay, so let's see if we can go a little bit to the Laplacian. Here we have another example, right, of an elliptic questions, right? You have here some bars on circle going up and down, right? Solid liquid temperature. So basically you have this circle, and then here you have a surface where there is a separation, right, from the solid liquid temperature T, right? So here the T is positive, right? And here the T is, it's my fault? No, okay. And here is negative, right? And so there is this separating this place, right? Like you are seeking a temperature, right? So that this is a fluid, for instance. And so you are looking at the temperature, and there is this point. There is not a separation for another reason. It's just that the temperature was negative below, and it is transforming above, right? And so this is the changing surface, okay? And so here it is, initially at the solid region at temperature T0 less than 0 with a free boundary surface, right? This one, right? Which is the one that separates, right, the capital T of x little t, because it is, the surface is changing in time, right? And this is the T of x t equal to 0 is what happens in this surface, which is evaluation, right? So the temperature in liquid region evolves according to the heat equation, right? So according if it is negative, then you have that the change, it is here, right, is a little bit what I said at the beginning, that instead of doing the Laplacian, you have the dij of some quantity that gives you more or less what is happening. It's not just the direction, how things are bending, right, which is this dij of x, right, which in the classical case is just 1, right, or characteristic of k, right? So, but here now it is, as I said, as a variation, d of xj of this coefficient kij of x, dx or djx, okay, of the function t of x and t, right? In other words, this is evolving. At the beginning looks like there was no t, but now we are saying, no, we are going to look at a case where the surface is evolving, right? And therefore, that's what the equation that you are interested in is not anymore the Laplacian, but it is this going up, okay? And so, let's see, how did I get a new line? No, you push that, pardon?
No, it's just a pointer. It's just a pointer. It's only pointer. No puede pasar.
That's what I was saying. Okay. Maybe it's my fault. Okay, well, but I don't want to squeeze now. In a little while, I'm going to squeeze now. Let me get to a second problem, right? So the first one was this surface swim up. This is a family of things that are translating upwards, right? As you can see from this, now we are looking at a surface, at a function, right, that is moving upwards, right? And of course, to make it nice or at least interesting, right? In different lines, it moves with a different velocity, right? But this mathematically is very close to the first example, right? So we have this movement here, right? And if you you cut the translation, then what the picture that you say is this distribution, right? Like saying near the center, the velocity is smaller than near the edges, right? And then it says here the nearby partitions will drag and accelerates the particle at space-time positions, right? So you have x and t, and the particle accelerated in a different way at some xt, x1, t1, and at t0, t0, right? So it's like a, oops. Okay, so basically it's as I said here, it's a fluid, right, flow with some velocity phi, right, and this velocity v is a velocity of x and t. And then how does one express these diffusion equations mathematically, right? One possibility is to compare the average velocity v of yt in a tiny ball, right, b epsilon of x0 around x0, with the actuality velocity v of x0 t, and to take the quantity, the average, right, of v of yt minus v of x0 t dy, right, b epsilon of x0. In other words, I am at x0 and I look at the little neighborhood, right, this y is a little neighborhood around x0, right, and then you are looking at the velocity in this little circle, little because there is this epsilon there, right, that is saying this is a little circle, right, and so what I'm looking is here as the velocity at here, I think, in fact, this picture more or less said, here is the x0, right, and here is the y, and the y's near x0 are going faster, right, and it is what is this in this formula, right, that is this average of the velocity at yt minus x0 t, right, and is positive, because this is the notion of diffusion we want to use in this case, okay? In other words, you can get different, what is it, you push up, what was it, how do you,
Strong push.
Well, how do I move it up? Okay, thank you very much. I have somebody that helps me. So a way to see diffusion operators as averaging, right? So we have these examples of what are diffusions and things like that. So now we want to go more more inside the mathematics of it, okay? So basically, we want to make a more just description of what is a diffusion operator, right? Averaging, okay? And so basically, a way to see the integral averaging as a diffusion process in the heat of fluid equation is to introduce the Laplacian PD operators. So the Laplacian, right, it was, in the general case, we got a generalization of the Laplacian. We just get the Laplacian, right, uxx plus uyy or something like that. Okay, so here we have, in this case, right, we have, this is an average of the Laplacian, right, and then we go to 0 and you get the Laplacian in some sense. So basically, you will take u of x plus c, so we are doing the averaging around x at x, right, so basically you are taking, the discrete way to do that is you are taking u of x plus h minus u of x, so x is frozen, right, well, pseudo-frozen at this point, and then you have u of x plus h minus u of x, that is u of x at the surrounding against u, right, and then so this is making an averaging, right, because you are making this sort of integral, so the h is in b epsilon, as it says here, so the h makes u of x plus h to be around u of x in a little circle, right? Differential of h, that is the things in the little ball, right? So basically, I'm looking at the average, right? If you take this and you averages with the point, the little point y around 0, then basically what you are computing is the sort of fractional Laplacian in some sense, right? That is u of x plus h minus u of x dh, right? And in the kernel of in the place of size b epsilon, but then you divide by b to the by epsilon square to make really an average, right? So you have they are averaging. You want to solve in some sense the Laplacian, right? And then you approach it by the averaging. Here you take an epsilon, you are doing the average, divide by the average square, right? And then you make epsilon go to 0. And when you do that, what do you get? Is the tangential Laplacian of u, right? You have the trace of dij of u of x, or what it is the same, the Laplacian of u at x, okay? So the important thing I want to tell you is, right, it is an interesting, important thing is this way, right, of approaching the Laplacian, because it has many applications, right? Like if you have a medium, which is not just like what corresponds to the Laplacian, but it has, you throw some quantity of something, and that makes a small variation. Instead of being the Laplacian, it's a tiny average, Laplacian type averaging, right? This, in some sense, is much more easier to understand, because to understand point-wise, this looks okay, whatever, but to describe something that is interaction, like I said, between the points, right? As the Laplacian, it is like a second point, the second derivative, which is, it is hard to decide that this corresponds to an interaction between myself and the people around, right? I mean, okay, uxx, right? While if you look at as a small averaging, right, then there starts to be important interaction, right? I am here and I have this I can do from myself something to the people that announce me, and each one there can do the same again and again and again, right? So it is very important to really understand better not just the Laplacian, but the fractional, what is called the fractional Laplacian, right? So a more general situation then is this non-local diffusion equation written in this form, right, where you are having now, I am going to write it in this form. I'm going to take ut of u of x0, that is fractional Laplacian part, and then I'm going to look at the average, I get at the average of u of x, u at xt minus u of x0 t. So now the time is fixed, and I'm looking at the averaging in space, right? And then, okay, and then what do I have for this Laplacian? And so I said, like, I like to understand how things happen when I have this special case sub sigma of y minus x0. So it's the averaging, more general averaging than what I mentioned before, right? And depending on this sigma, what you have here is not necessarily the Laplacian of the function, right? But some averaging of Laplacian times averaging, right? So it's Laplacian to the sigma, let's call it sigma of u of x0 t, okay? So basically here, the picture is that I am, let's say, for t fixed, right? What you have is all of these rings, right, which are given by this k sigma, right? And so gives at the point x0 of what is going on at y, okay, for all y belonging to r to the n, okay? Note that when sigma is 1, the average operator becomes a Laplacian, but many times you are interested in non-type of Laplacian, but places where the averaging, the volume, the quality of the averaging around a point can depend very much on the position or things like that. So it's not just the Laplacian, okay? So, so typical. So let me show you some typical examples of that, right? So surface diffusion in free boundary problems in probability integral diffusion appears when considering jump processes, right? That is not continuous, that is Levy process in optimal control, game theory, and finance models. Okay, so there are many applications where this non-infinitesimal, non-local media appears. Okay, so in continuous mechanics, they appear when considering surface diffusion or surface discontinuities. That is when they are jump on the boundary. That perceive long ranges from the interactions taking place on both sides of the surface. Fundamental examples are the quasi-geostrophic equations for ocean atmosphere interactions, that is where there is mixing between water and solid parts, right? Semi-permeable membranes and planes cracks propagation. Okay, so it's basically cases where there is it's not infinitesimal anymore. The mathematics, right? There is averaging and jumping and so on. So in fluid dynamics models for turbulence flows or particular integrations bouncing through random media, that's what I was saying of this thing nearby that you want to average, and difference scales. So here are some of the classical authors, right? So surface differential processes included by, so here you can say, right, surface difference processes induced by interfaces, right, and interface problems study configurations consisting, okay, so let me go a little bit for a second. Integration problem study configurations consisting in having a diffusion equations with two or more different media. So in other words, with different distance and so on. Think of the solid ice, right? When you have ice and liquid water, then it was a solid and the liquid, and there is this surface of melting, right? That they make an important role there. Okay. Schematically, the solution of such a problem, that is, you have the melding things, then schematically the solution of such a problem for any fixed time describe a surface S in a boundary of interaction between the diffusion equation on each of the surfaces. In other words, I have this differential, and here we have the medium A, and we have to have the medium B, and then this separation that may evolve in time, as we can see. So we have this free boundary surface, is called this. So an important family of examples concerns surface diffusion. In other words, we have the separation, right, and then we want to see how that evolves. Okay, so in that case, quantities that live on the surface flow through a membrane. In other words, this has the membrane, and things flow through the membrane, and affected by long-range interactions, could be here, right, through media A and B at both sides of the surface S. In other words, okay, great. So here, this is as I said, this is a much more interesting. What we are looking up to now was circular things and very special, and here now becomes more interesting things where you have two media, right? I mean, maybe one solid and not so solid, or water, or with different properties, right? And so you have this surface of discontinuity, right? That may want to try again, to move again, right? Like something that is bending or something like that. So in this case, quantities that live on the surface, right, flow through a membrane. So you have this membrane, and you have the medium and the other medium, right, and are affected by long-range interaction through media A and B. So you have this medium A, right? This can be some quantity with some properties of melting or something like that. and this is another property of melting or of heating or something like that, and then there is this separation, right? And so here the interesting thing, that is the movement or the evolution, is in this jump place, in this surface of discontinuity, right, from medium A to medium B, okay? In that case, quantities that live on the surface, right, flow through a membrane, that is the membrane, right, so a membrane have the surface and are affected by long-range interactions, that the interaction through media A, so you have and B. In other words, media something happens A, happens in B, and then that's what makes interesting is what happens with the surface in between. Okay, oh, did you just move it? Yeah, great, thank you. I just cannot look. Oh, just okay. So movement by integral curvature, right? Which was the surface I said. So this movement by integral curvature and surfaces minimizing non-local energy. Okay. So let's look at this problem, right? Okay. Okay. This has changed. Okay. Class. And so classify minimal surface. So for set of finite perimeter, right, minimal surfaces are those obtained by a minimization process stating. So you have any local perturbation of volume D. So this is volume D, and suppose that this will be horizontal, right? Like here, some solid thing, and above some liquid things, and then there is some then they bend in a particular initial way, and as time goes by, the bending may be more and more, right? So any local perturbations of volumes D increases the perimeter, right? Because the perimeter is the bending, right? Is the perimeter. So here we will have. So here the geometry is we have a sigma, right? This sigma, right, which is the volume domain. So you have here the sigma, right? The solid thing is the volume domain, and S, that is boundary of D of omega, is the minimal surface. So you have the bases and the edges, so it's a minimal surface, right? And the is based on the concept that either or, what happens is that either prescribe any change on boundary of omega by the perturbation of boundary of D, right? So we have here boundary of omega, and here we have D. So when D moves, that perturbs delta sigma, right? Without taking into account what is outside the volume perturbation. So there's a D is the mathematical problem where basically you have what happens with D and how that moves the top. And I'm saying nothing of what happens above, right? So this is one example, right? So either prescribe any change boundary of omega by the perturbation boundary of D without taking into account what it is outside the volume perturbed D, that is above. So since the classical mean curvature equation is local in this case. Or we can quantify the zero mean curvature condition as a higher order density, cancelling on omega and the complement of omega in the ball BR of x0. Okay, so can I click what's here? Okay, so that's the surface. We have the surface S that was in the middle, right? And which is the boundary of this omega. In other words, in this case, the heavy thing is not on the surface but on below, right? And the surface, gives a quality of how the edges, the edge of S on the top evolves, right? So here it says then the average of such a ball, BR of x0, have different order depending on the surface S regularity, right? So the surface, remember, was the one like that in the middle. If S, which was the boundary of omega, has mean curvature 0, it satisfies smallest average on the ball BR of x0, right? So you have that the average of BR of x0 of U of x is equal to the average of BR of x0 of the boundary of omega on the capital of sigma, the volume of sigma, minus the volume of complement of sigma dx, that is equal to the O of R. So basically, here is more or less a little, a middle picture, right, where you have this separation. Here you have the D, the omega, the lower omega. Here we have S, the boundary of the omega, and then this, how this evolves. It is elliptic or parabolic thing we want to consider, okay? But if S of 0 is the boundary of omega for any smooth volume perturbation D, or if the surface S equal boundary of omega is just Lipschitz, then the resulting integrals have higher order, changing the scaling of the observations as a function of the ball radius r. So in other words, there is here some variation of it if this structure, right, is not just solid, like evaluating, okay? So here we have again our friend, right, which was, you remember this was the averaging, right? You have the U of the x, right? And you have this quantity B of R of x0, right? U of the x, right? And this is equal to the average, remember this integral with the line, right? Of capital sigma minus capital sigma complement, right? So we have the average. This quantity is equal to the average on the ball of radius r of this difference of capital, right, on one side and the other, right? So remember, this quantity is equal to this quantity that looks at the two sides of the capital, right? Is the one below and the one above. And it's equal to the average in terms of R is the radius, or the average of one respectively, okay? So it's the various looks of seeing these equations, okay? So the surface Laplacian along boundary of omega, so this Laplacian along the boundary of omega of U is equal to Laplacian on S of the characteristic of omega minus the characteristic of the complement. That's basically giving the jump of U across the boundary of omega. Okay? So, so we are interested in the case in which that is 0. There is this cancellation of the part above with the part below. Okay. So here there is another, this is in some sense maybe the most interesting to my taste case, right, which is the different happenings when the equation has different energy, right? And so here we have two examples, right? So here we have in this disk, let's say, of radius 1, here we have a part which is 1 here, minus 1 or 0 here, and this thing in the middle. And this thing in the middle is like a slight tilted thing, right? And so what is the way to describe that? Well, this says that we have these functions whose Laplacian, it is 0 here, it is 0 here, maybe it is 0 here or not, but it has this jump over here, right? And so this, basically you look at that, and that it is maybe interesting, but you don't know very well why. And this is interesting when you see here the first derivative, right? It is smooth here, and that is the gradient is smooth here, and here has this jump. But really what is interesting, at least for mathematics in many cases, what happens when this becomes steeper and steeper, right? If I do this steeper and steeper, we are converging to something which is 1 minus 1 and vertical 0, which means that the derivative now, right, here says jump over here. The derivative here is 0, but here is jump becomes vertical, okay? And therefore, if the limit of this, it is interesting because this is a general surface here, but what happens with the function is that it's elliptic and nice when it is flat, right? But the second derivative is infinity on this surface. So as epsilon goes to 0, the minimal surface the minimal surface here, let's see here, I think it's explaining better, right? The minimum energy function, u epsilon, gets very close to 1 and minus 1 with an epsilon narrow region of phase change, which is this 1, due to the dominant potential f of u sub epsilon, whose organization is dominated by the free energy, the integral of the gradient of u, so the laplacian of u squared. So the minimization solution limit. So in this first case, right, you have an example of a function that is in the limit it is bounded, but it has a discontinuity due to the first derivative. So that means that you want to see how nice is this function, it has a Laplacian sense and so on. Well, what you have is that it's very nice here, but it is not very nice everywhere because it has a jump on the derivatives. It's just that the derivative is 0, but it has a jump at this point. So this is one example of perturbed energy functional. In other words, when it is like this, it's a nice energy functional, but it is perturbed in the sense that it has this jump at the end, which is here you can see it in this epsilon, right? When epsilon goes to 0, right, then this is okay, right? This is okay, but here you have the 1 over epsilon, the integral of r of n, that makes the jump of the derivative, makes the derivative infinite there, okay? So this is a very interesting possibility. Another type is if you have something like this, right? So this is another minimizer solution limit, right? So when epsilon goes to 0, okay, let me see. You have u sub t, and here what you have is that that you have the boundary of omega and of omega, right? And so the boundary moves proportionally to its minimum curvature, okay? So here what we have is this surface that has a curvature like this, and then it sort of bends here. It's not as bad as this. This here becomes vertical. Here this produces just an angle, okay? So here you have the boundary of the omega, which is here is for the red, right, and the omega, on the characteristic of omega, right, and so then they have that this bending becomes make an angle over here. So this is not as bad as this. This is more like Lipschitz, right? Like this is discontinuity, okay? So, so let's look a little bit careful about these formulas, right? We just look at the pictures, and that was nice, but let's look at the free boundary detection for continuous discontinuities. It says Lipschitz limit case. So there is the first one, as I said, there is the limit case where the derivative has a jump, right, but it doesn't go to infinity. And in that case, what you have is that the energy, right, is the integral of Rn as the gradient of u epsilon squared plus, and here you have the characteristic of the set where absolute value of u was less than epsilon, right? Remember, there was this curve thing in the example before, right? So this is the standard energy that happens below in the curve or on the sides, and then there is this this line, let's say, or curve where there is this jump, but not discontinuity. It's just that the function has at this level and then just takes another direction, but it's just Lipschitz, okay? So you just Lipschitz, and so when you look at the energy, you look at the gradient of u squared, which is, since it is Lipschitz, it is nice and worse, and then there is this area, right, where the set of u is equal to 0, right, and so this is the lateral thing to the curve, right? So this is a much milder thing than the case where the thing was just broken, right, from the u. Here the u has bounded Laplacian, in other words. You have the part where u is 0, and then this part where the gradient of u has some quantity acceptable. The results extended to the Giorgi theory for double well potentials, right? The solution u is Lipschitz as the one before, but has a more information, has that, and along the interface S, right? That is, you have something flat, and that in the Lipschitz case, you have something, let's say, for instance, flat, and then something which is curved, or that makes a round ball and keeps going, right? And so the solution in that case has a gradient of a positive square, the negative square, so this, and then equal to h of a, which is the mean curvature of S. So it is a case where you have a bending on one side, there's a Lipschitz on one side, a Lipschitz on the other, right? But you don't want to say that what happens when one gets together to the other. So this is a nice Lipschitz theory, right? Then there is a Giorgi, okay, example, like in Giorgi the surface S is smooth except for a set of dimension n-8. And I never knew very well why this was so n-8, but this is what the Giorgi wrote at this time, right? And so it's so as I said here, right, it depends on the topology generated by the surface segregation potential. Okay, so this is nice, classical, the Giorgi theorem. Okay, see, there is a Lipschitz one, right, and the Lipschitz one is straightforward by using a suitable multiple of the distance function, distance from x to s, as an upper barrier for u. That is, you have x and you have this s bounding above, right? As an upper barrier for u. Then u is Lipschitz again, and the free boundary condition, absolute value of gradient u is equal to capital O of u, that is bounded. Okay, so whoops, did you jump a lot or a little bit? Jump a lot? Okay. But anyway, let me just tell you about the little bit thing we saw before, right? that is interesting because it's a family of Lipschitz variation, right, of the functions. In other words, you have surfaces that can be C2, C1 plus alpha, and so on. But there's this, in reality, right, is a very important and usual things is when you have some surface here where something is constant value or constant strength or whatever, but there is in some particular things there is this jump, but not the jump discontinuity, right? It's more like that you have this surface quantity and you push on it, right? And the way you push on it, it creates you different variations, right, of the change. But usually you expect to be okay. You can expect to be just jump, can be to have tangents of order 1, that is at an angle, fixed angle, right? Or at a complex angle, right? Complex because they are more bending than the linear, or others which are interesting because they are flatter than the linear, right? And so these are different and very important things because if you think a little bit, you can find half a dozen things that have this form, right? That is, I mean, if you have an egg, you cut it in half and put it there, right? Has this angle, Lipschitz angle. You can take a material, that you bend, right? This is a metal thing. You can bend it, right? And then can be Lipschitz, right? Or even if you bend it tangentially, it's C1 alpha, right? So this is a very general theory of that has been developed by many important mathematicians through time. Okay, here it is a little bit what I said, that you have a harmonic function which is Lipschitz along a boundary surface where it vanishes, or that's what the cases I say, right? Or they have the terms where the nu plus square minus u minus square is equal to 0. So there is, I think it's an interesting thing that you can look at it carefully. It's not terribly difficult, but it is interesting. It is interesting to know that things exist because there are many applications where you have medias that have an angle, right, of separation or tangential separation or vertical separations. And different, depending on the things that you are interested in study, then those are different things. Could you move it? Oh, you did already? Wow. I cannot look at our size. Okay. Okay, let's go directly here. Well, the previous one that you proved is a nice. Can you look that this is a nice picture? Okay, this is the separation of two. Yes, no, I already talked about that. Okay, so the product of energy. Okay. I think, this is more or less related to what I mentioned of you having this surface which is horizontal and then has an angle, right? And I say this is a little bit more of a variation of what I did before, right? Here, Sobolev had a more delicate description, right? Mathematical description of this situation, right? Here we have the gradient square at the top and xn minus 2 at the bottom, and you can, if the ratio between the gradient and the function is appropriate, then you have a C alpha or C1 alpha surface separation. You can look at the computation and you can see here in this case something that you have that the function for r bigger than s, the function is less than this angle, right, times this quantity. And if you look at it carefully at this quantity, you have an idea of the angle, right, of a function between 0 and a function there. Okay, so there's not too much time, but I think you should, if you have some time, it is something very interesting and learn, something that is worthwhile to learn and interacting very well because it has many applications of that order, okay? And what else do you have? Okay, that's another of that type, right? Here it has the Giorgi. I told you the Giorgi has these things which are flat and then come at an angle. Well, here is one. The Giorgi type iteration, right? You have a sequence of points. So here you have a picture of these things, right? So you have a case where you have the flat part, right? The flat part, and then you have the part which is coming at an angle from there. From in this picture goes from there with an angle and below to an angle. So it is the case where you have two different angles, right, coming together. Others, as I meant, that can be constant and a curve. So I see they are all of these variations, okay? And they are all sort of have important applications in anything, right, that you are looking at a plastic something and you bend it, right? You have this situation, right? If you have you want to eat the soup, right? You have this metal thing on the top, and then the basis is another one, and there is this angle, right? So again, there, and if the angle is very little, it's probably easier for a kid. If the angle is bigger, the older person can enjoy it better, right? So it is important how the mathematics of this type, right, are over everywhere, although you don't pay too much attention of that. Okay? So here it is, elliptic is encountered in the free boundary surface as Lipschitz, and high C alpha regularity follows. Okay, so you have the different possibilities. Okay? Pardon? Yes, yeah. Okay, so this is the wrap-up? Okay, good. This is good enough? Okay. Then to natural questions arise, right? So I think it's more or less what I was saying, how to extend these concepts to sigma fractional free energy for potentials f of u equal characteristic of the set where absolute value of u is less or equal than epsilon. So this is one of, I told you there is a bunch of different ways in which two things come together, okay? And then the first one, the first one is a classic one, right? So f of u is a characteristic of the absolute value of u less than epsilon. That is when the but when the u is close to 0, right? And the next one says, how are the corresponding Euler-Lagrange equations and free boundaries for fractional calculus modeled? So you can take and look at the first thing, and you can even take a piece of place and start to drawing the sizes and what is the possibilities to make this equation with the bases that wiggle, right? You can say, okay, I got this characteristic, but I'm not saying that there is regularity, X regularity for the U, so you can have something that wiggles, bling, right? And it is 0 in part of the blending and another in the other. And sometimes if you can add a little properties, like asking that the place where U is 0 is Lipschitz, so you cannot have a thing which is very narrow where U is equal to 0, so that would be probably a very important application if you are really doing some materials, you're doing a square something, right, with material to have a good understanding of when you build these pieces and paste them together, right? What is the ways you want to a metal to bend it in an acceptable thing, that could be just curve, no more than curving, except on an edge, where it makes an angle and things like that, okay? So what you look at it and seems like easy for a person that is bell milking is non-trivial at all. So let me thank you very much for your patience. Thank you.